Hey everybody, today we're doing an example of solving a rational inequality. Now, I'm doing a particular problem here, but the procedure I'm about to do is completely general. It'll work for any rational inequality, where one side is one polynomial divided by another, and the other side is zero. If we don't have a zero on the one side, before we do the process I'm about to do, we got to move everything to the other side before. Okay, so the sort of function we have here on the left, a rational function, is a nice one. One polynomial divided by another. We know that a function like that can only go from positive to negative at two kinds of points: at the zeros and at the places where the denominator is zero. In other words, points that aren't in the domain. So all we really have to do is figure out where this function is zero and where it does not exist to know the only candidates for the places where this function can change from positive to negative. And that's a pretty finite list. These are called cut points. And we have three of them here: 2, -4, and -1. Let's write those from smallest to largest. -4, -1, and 2. Great. So those are the only places where the function could possibly change from positive to negative. Let's write those on a number line to get a visual on what's going on here. -4, -1, and 2. And those are all x values. So on each one of these individual intervals, this function is either positive or negative, not any kind of mix of the two. So if it's positive at one point in here, it's going to be positive at in the whole interval. If it's negative at one point in this interval, it's going to be negative on the whole interval. So the idea is, let's just take one point in each of these intervals, plug it into the function, see if we get something positive or negative, and draw conclusions from that. Now, I'm going to explicitly rewrite the function that I'm testing right here above the number line. Here it's just recopying things, but when we start doing calculus problems where we have a function and one or two derivatives floating around, it's important to keep in mind what function we're actually testing in, which one we're interested in. So it's a good habit to get into now. Okay, so let's pick a point in each of these intervals. Let's start on the left. Let's look at x equals -5 and determine if this function is positive or negative. Now, I want to plug in, but I don't really care about what the value of the function is. I only care about the plus or the minus. So when I plug in, I'm not going to think in terms of actually computing numbers. I'm just going to think in terms of pluses and minuses. When I plug in x equals -5, -5 minus 2 is negative. -5 plus 4 is also negative. And the denominator, something squared, is always going to be positive. So negative times a negative over a positive, that's positive. Great. Moving on. Let's look at x equals -2. When x is -2, negative, positive, positive. Negative times a positive is negative, divided by a positive is still negative. Let's do x equals 0 in this third interval. I'm trying to pick points that are as gentle as possible when I plug in. Any value in here would do. We may as well pick round numbers. 0 is as round as they come. Negative, positive, positive. Okay. Finally, x equals 3, positive, positive, positive. Excellent. We're interested in the intervals in which we get pluses. We want to know where this thing is greater than 0, where it's positive. Here and here. Unfortunately, we're not quite done yet. We know that on the inside of this interval, the inequality is true. Here it's false, here it's false, here it's true. But so far, we haven't said anything about what happens at these individual points. So we need to check these manually. We have to think about x equals -4, -1, and 2 by plugging them into the original function. So f of -4, when I plug it in, I get 0. So that's not true. That when x is 0, this inequality is not true. Let's indicate that by putting an open circle here at the value. At f of -1, the function isn't defined, does not exist. So the inequality is not true there. I could put an open circle here, but a lot of times you'll see a sort of vertical asymptote drawn on these sign charts to indicate that the function isn't even defined there. It's got a vertical asymptote. Finally, let's check f of 2. When I plug in 2, I get 0. And again, the inequality is false there. Now that I've checked all of the individual cut points, as well as determined what happens on the insides of these intervals, I'm ready to write my answer. Let's do it in interval notation. Overall, I get from -∞ up to -4, union from 2 to +∞. And that's the solution to this rational inequality.